Hi folks, we're going to take a look at number 16 from page 146. So here we've got a north-south highway intersecting an east-west highway. So keep in mind here that they're going to be at right angles to each other. So it says a vehicle crosses P, okay, this point P at 1 p.m. and travels east at a constant speed of 60 kilometers per hour. Okay, so before I draw my diagram, I kind of want to see where everything's going to be located. So I know I'm going to be traveling eastbound, so probably don't need to leave too much room on the left side. Let's take a look at the other car. At the same instant, another vehicle is 5 kilometers north of P and is traveling southbound at 80 kilometers an hour. All right, so I think what I can do is draw my point P somewhere here. Leave myself lots of room on the top and at the right. Okay, so I have one car that's leaving P at the given time, okay, at 1 p.m. And then I have another vehicle that's starting off 5 kilometers north of P and moving southward towards P. Okay, and what we want to figure out is the time when the two vehicles are closest to each other and the distance between them at this time. Okay, so notice here I don't draw this car reaching P because I'm not sure when they're going to be at their closest. So I want to draw the most generic moment in time possible. So car A has moved a certain amount towards the east and car B has moved a certain amount towards point P from the north. Okay, so this line here represents that thing that I'm trying to minimize. I'm trying to minimize this distance. So hopefully this type of question looks familiar, and I notice, hey, look what I've got. I'm going to have a right angle triangle here because they did tell us that it's north, south, east, west. So I know that this length here is going to be the third side to a right angle triangle. All right. So the question is how can we describe these two sides to connect it to the distance that we're looking for? Well, this is where we're going to use the fact that the cars are traveling at constant speed, so we know that the speed is equal to the distance over the time, so the distance is given by speed times time. Okay, now the thing is I don't know how much time has elapsed at the point where they're closest, so this is going to remain our variable, but we do know the speeds of each vehicle. So the speed of this one here is 60, so the distance travel is 60 times t. All right, now this car has traveled 80t, okay, but this is not the length that I'm looking for. I'm looking for that one there. So luckily they told me that the distance it started from was 5 kilometers north of point P. So that means that this side of the triangle is 5 minus 80t. Okay, and now I have enough information to write a formula for this distance, okay, with respect to one variable. And kind of nice that the variable that it's given with respect to is time, because that's one of the things I'm looking for. So here we have d squared is equal to 60t squared plus 5 minus 80t squared, which of course is just Pythagoras. Now, had we been doing this problem before we had looked at implicit differentiation, I would have solved for d here. All right. But since I'm doing this video after we've looked at implicit differentiation, I'm going to use implicit differentiation here. So I'm actually not going to solve for d. It'll avoid having to deal with square roots. All right, so what I'm going to do now is take the derivative with respect to time of both sides. Normally I probably wouldn't write this this step here, but just so that it's very clear what I'm doing. Okay, so here, remember I'm taking the derivative with respect to time, so I have to use the chain rule. Okay, so first I have to take the derivative of the outside function, which is d squared, so that's just 2d, and then the derivative of d with respect to time. Derivative of the inside function with respect to time. Okay, and here, everything here is already given in terms of time, so I could just take a derivative as usual. Okay, and what I'm going to do is I'm just going to use the chain rule in both of these. I'm not even going to bother multiplying it out. I certainly could, but I'm going to take the derivative of this thing here. So this is like my u squared, so 2 times 60t times the derivative of 60t is just 60. Okay, plus This one here, chain rule really comes in more handy. I could have done this by first multiplying it out, but here the chain rule is handy. So 2 times 5 minus 80t to the exponent 1 times the derivative of 5 minus 80t is just negative 80. All right. And here I can divide 2 out to both sides. So there you go. Makes my life a little easier there. So if I'm looking for the derivative of the distance with respect to time, that's just equal to, so now I'll clean this up a bit. So 60 times 60, that's 3600t. Here I've got 5 times negative 80, so minus, it's going to be 400. And then negative 80 times negative 80 is positive 6400t. Okay, all over, and I'll just divide the distance to the other side of the equation. But remember what I'm looking for, as I'm looking for where the derivative is equal to 0, because I'm trying to find the extreme value. Okay. Oh, and I just realized here something that we didn't do is right at the beginning is we did not give our domain here, but our domain is just going to be, well, t has to be greater than or equal to, or greater than or equal to 0. Okay. We don't actually know when. Actually, I suppose we could give an end time, because I suppose once this car reaches this point here, well, there's no way it's going to get any further. It's going to get any closer at that point. But let's just leave it as it is here. Okay, so here, I only need the numerator to be equal to 0. I don't care about the denominator because I've got a fraction. So this distance, I don't need to calculate it. It's not of interest to me. So what do we have? 3600 plus 6400. So it's 10,000 t minus 400. So t is just going to be equal to 400 over 10,000. Okay. Get rid of those. So it's just going to be 4 over 100. So 0.04. Okay, now let's just test that this is indeed a minimum value. All right. So it's our only critical point, so 0.04. And so here, let's put, I don't know, 0.01. Okay, so let's take this derivative here. So this is a distance value. So this is always going to be positive. I essentially just have to look at the numerator, okay, for my sign. So if we put in, and I'll take the simplified version, so 10,000 times 0.01 and then minus 400, okay, that gives me a negative value. And then let's take 0.05. So 10,000 times 0.05 minus 400 gives me a positive value. Okay. Now, since that was my only critical point from 0 to infinity, okay, we see that this function is decreasing all the way to my local minimum, and then it's continually increasing afterwards. So this is indeed an absolute minimum on this interval. Okay, so now let's figure out what they're asking us now that we've found where our our minimum occurs, and they want the time, and then they want the distance between them at that time. Excuse me. Okay, so I could say 0.04. So remember, this is in hours because the velocities we were working with were per hour. So if we want to put it in terms of minutes, it's just 0.04 times 60 minutes. Okay, so let's calculate that. 0.04 times 60, 2.4. So it's 2.4 minutes. So let's start with when it happens. Okay, occurs 2.4 minutes after 1 p.m. I guess I could calculate how many seconds. That's not a big deal, but I'll just leave my answer this way. And the other thing they want is the distance between them at that time. So now let's find the distance. So since I'm actually looking for the distance, I will take the square root. So it's the square root of 60 times 0.04 squared plus 5 minus 80 times 0.04 all squared. All right, so let's calculate that here. So 60 times 0.04 squared, and then here plus, let's put this whole thing in brackets, 5 minus 80 times 0.04 all squared. Okay, and then square root of that, well, that's just going to be equal to 3 kilometers. All right. So there we have it. It occurs 2.4 minutes after 1 p.m. and their closest distance to each other is 3 kilometers. All right, so let's just do a quick recap. So again, good diagram is always important, okay? Now remember that the first car was leaving from point B and moving in the eastward direction. The other one was starting from the north, moving towards P. When you draw your diagram, you want to draw some random point in time. So you don't want to kind of draw it so that it actually reaches P. It's gone some distance, you don't know how far. And then from there, we were able to come up with a right angle triangle to determine a relationship for the distance, okay? In this case here, I decided to use implicit differentiation. I certainly could have taken the square root of both sides and used my traditional differentiation methods. All right, that's it for this one.